Okay. So, yeah, so as Rudrada is asking, let me just give a brief review of the different kind of uh, curvature, metric spaces with curvature bounds. So what are the different kind of spaces we have? So, uh, so let me see. Okay, so first of all, if we look at metric spaces, so they don't have to be manifolds, okay? Then, first of all, it's useful to define what is a geodesic in a metric space. So, a geodesic is an isometric embedding uh, of an interval into the space. So that means a map gamma from an interval in R into X such that the distance between gamma S, gamma T is equal to mod S minus T for all ST in I. So this is a geodesic in a metric space. Yeah.
But it may not exist, right, in any arbitrary metric space.
Correct, correct. So we say a metric space is geodesic if any 2 points can be joined by a geodesic. So for all x, y, and x, there exists a geodesic gamma from an interval of length t into x such that gamma 0 is x and gamma t is y. So here t is equal to the distance between x, y. So for example, by the Hoffe-Rino theorem, any complete Riemannian manifold is geodesic.
Okay.
So let me make one small remark here that in a Riemannian manifold, we've defined geodesics as curves with zero acceleration, right? That means, so in a Riemannian manifold, gamma is a geodesic if gamma double prime, what is gamma double prime? It is the covariant derivative capital D dt of gamma prime, this is identically 0, right? This is a geodesic in a Riemannian manifold. Now, this may not always be a geodesic in the sense of metric spaces. For example, if you take the sphere S2, right, then the longitudes are geodesics in the Riemannian sense. Their covariant derivative of the tangent vector is 0, right? Now, here though, if I take 2 points, let's say the North Pole and the South Pole, then as I go till the North Pole, the distance between any 2 points, say gamma S and gamma T, this is equal to mod S minus T. Okay, this condition holds. Okay, up to the South Pole. But when I go beyond the South Pole, right, then if I look at, let's say, the distance from the North Pole to this point, some gamma T here, right, then the distance is not, let's say n is equal to gamma 0. So if gamma was a geodesic, the distance from n up to gamma t would be equal to t, right? But in this case, when t is bigger than pi, then the distance becomes pi minus t, right? This length here, this is pi minus t. Okay, this is the shorter path, right? So the distance is the shortest length of the shortest path. So the shortest, this geodesic is no longer the shortest path when time is bigger than pi, right?
Right.
So this is not a geodesic for all time, in the sense it's not a geodesic if I consider it as a map defined on, let's say, on the whole real line, then it is not a geodesic. Instead, what it is a local geodesic in the sense of metric spaces. So gamma is a local geodesic in the sense of metric spaces. So what is a local geodesic? That means that for all t naught for all t in the interval I, there exists epsilon positive such that gamma restricted to t minus epsilon to t plus epsilon from the interval t minus epsilon to t plus epsilon into the metric space X T. This is a geodesic in the sense of metric spaces. Okay, this is a geodesic.
Also, sir, as long as we stay inside the inductive radius, there is no problem, right?
Yes. So this is a geodesic. This is an isometric embedding. So the point is, what I'm defining as a geodesic in a metric space, that is stronger than what is a geodesic in the Riemannian sense. So what turns out to be true is that so if X is equal to a Riemannian manifold, and D is equal to the distance function on X. So induced from the Riemannian metric. Okay. So that means the distance between points xy is the infimum of lengths of curves joining xy. Then given gamma from an interval I in 1 into x, let's say a smooth curve, then gamma is a local geodesic in the sense of metric spaces, right? If and only if gamma is a geodesic in the Riemannian sense. Okay. And
Unit speed geodesic in the ring.
yes, correct. A unit speed. Yes. So, I mean, if I take a smooth curve, I can always reparameterize it to have unit speed. So let me just assume to make the statement neater, let me a smooth curve with unit speed, okay?
Right.
All right, so gamma is a local geodesic in the sense of metric spaces, if and only if gamma is a geodesic in the Riemannian sense. And gamma is a geodesic let me okay, let me take the interval to be a compact interval for simplicity. Yeah, so gamma is a geodesic in the sense of metric spaces. If and only if gamma is a length minimizing Riemannian geodesic. So is it clear? So geodesics in the sense of metric spaces correspond to the length minimizing Riemannian geodesics. Okay. Whereas general geodesics in the Riemannian sense, those are only locally length minimizing. Those are not necessarily globally length minimizing, right? So those will only be local geodesics in the sense of metric spaces. Is the difference clear? Yeah.
Yes, sir.
Okay, so for example, we saw this example, let's say on a genus 2 surface, say a hyperbolic surface, a quotient of H2, the hyperbolic plane, right? So then, we saw that given any 2 points, right? There will actually be infinitely many Riemannian geodesics joining them, right? But only one will be length minimizing. Okay, there'll be one length minimizing one, and there'll be lots of others which, you know, do all sorts of things before coming around. I don't know, they could go around like this and like this. I mean, quite a long geodesic, okay, before finally closing up and coming here. Okay, so the second geodesic is only a local geodesic, as a in the sense of metric spaces, right? It's not a geodesic in the metric sense. It's only a local geodesic. The first one, the length minimizing geodesic, is a geodesic in the sense of metric spaces. The other one is only a local geodesic. So is the difference clear?
Right.
Yes, sir.
Okay. So once you have geodesic metric spaces, then you can define what is called let's say a cat0 space. Okay. So what you want is a metric space which is geodesic. So XD is a geodesic metric space. Such that all geodesic triangles in X are thinner than their comparison triangles in R2. So let me explain what this means. So this means the following. So a geodesic triangle means a triple of geodesic segments whose endpoints match up. Okay. All right. So you have three vertices X, Y, Z. Right? And corresponding to this geodesic triangle, there is what is called a comparison triangle. So that means if I take these lengths, say the lengths of the sides are A, B, and C. So because we're in a metric space, ABC satisfy the triangle inequalities. So A plus B is greater than or equal to C, B plus C is greater than or equal to A, and A plus C is greater than or equal to B. And these are non-negative numbers. So from elementary Euclidean geometry, given three non-negative numbers satisfying the triangle inequalities, there exists a unique triangle in R2 with the same lengths ABC. Okay. So this triangle with the same side lengths is called a comparison triangle. And so let's call the vertices X bar, Y bar, Z bar. Okay, so here is our triangle delta inside X. And then we get a comparison triangle delta bar in R2. Now, what does it mean to say that the geodesic triangle in X is thinner than the triangle in R2? It means that if I take any 2 points on the sides of my geodesic triangle, okay, So say PQ here. Then since this side XY has the same length as the side X bar Y bar, right? There is a unique point P bar on this side, so that the distance of P bar from X bar is the same as the distance of P from X. Similarly, there is a unique point Q bar such that the distance of Q bar from X bar is the same as the distance of Q from X. Then to say that the geodesic triangle delta is thinner than the comparison triangle delta bar means that the distance from P to Q is less than or equal to the distance from P bar to Q bar. So the distance PQ is less than or equal to the distance P bar Q bar. Right. So similarly, can define a cat minus one space by taking comparison triangles in H2 instead of R2. Okay. So then you want your geodesic triangles in X to be thinner than the comparison triangles in H2. Okay. So this minus one here refers to the constant curvature of the model space H2. This has constant curvature minus one, whereas the cat 0 refers to the constant curvature of the model space R2. That has curvature 0 everywhere, right? Okay. So is the definition of cat minus one clear? Instead of taking the comparison factor in R2, you take it in H2. And request the same inequality is true. Okay, the distance between points PQ is less than or equal to the distance between the corresponding points P bar Q bar in the comparison triangle in H2. Okay. So actually, why were these defined? These so similarly can also define
H2 itself is cat 0, right?
yes, but that needs a proof. Yes, that's true. Any cat minus one space is cat 0. That is true, but that needs a little proof. Yeah, that's true. That's true. That's true. So if I take a triangle in H2 and then I look at its comparison triangle in R2, then the triangle in H2 will be thinner than the triangle in H2. In R2, sorry. The triangle in H2 will be thinner than the triangle in R2. That's true. Yeah, that's true. That is true. It needs a little proof. You just use the so for R2, you have the Euclidean law of cosines, and for H2, you have the hyperbolic law of cosines. So if you use those, you can show that the triangle in H2 is thinner than the triangle in R2. So it needs some Euclidean and hyperbolic trigonometry. That's all. Okay. So similarly, we can also define a cat minus k squared or cat minus a squared, cat minus a squared space for any a positive. Here you take the model space to have constant curvature minus a squared. So how do you get a space of constant curvature minus a squared? Well, that you can get by taking the space of curvature minus 1 and then dividing the distance function by a. Then the curvature gets multiplied by a squared. Okay. So if I look at H2 with the distance divided by a, then this will have a constant curvature minus a squared. All right. Okay. So I can call this, let's say, H2 minus a squared. Okay. So this, instead of constant curvature minus 1, it has constant curvature minus a squared. That's all. Okay. So then I can define a cat minus a squared space. All right. And then there is a theorem of Alexandrov, which is the motivation for defining these cat K spaces, that if X is a complete simply connected Riemannian manifold, such that the sectional curvature of all two planes is less than or equal to minus a squared, where a is some constant which is greater than or equal to 0. A could be 0. Okay. Then X is a cat kappa space, cat minus a squared space. X is a cat minus a squared space. Okay. So in particular, if the sectional curvature is less than or equal to 0, then it is a cat 0 space. If the sectional curvature is less than or equal to minus 1, then it is a cat minus 1 space. Okay. So for simple examples of spaces which are not manifolds, but which are cat minus 1, for example, you can take trees, metric trees. Any tree is a cat minus 1 space. In fact, a tree is any tree X is cat minus a squared for all a positive.
Yeah.
So in a sense, it is cat minus infinity. In a sense, a tree has infinite negative curvature. Okay. So, yeah. So this is a simple example of a space which is not a manifold, but which is a cat minus 1 space. And so, of course, it's cat 0 also. Yeah. So this is true. Oh, and I should say, yeah, so if B is bigger than A, then cat minus B squared is also cat minus A squared. Okay.
Right.
Yeah. So that is the thing. So, right. So here the important hypothesis in Alexandrov theorem. So completeness, we will always assume we always work with complete Riemannian manifolds normally. Now, what's important is the simply connected. What's important is the simply connected. That implies that the space is globally cat minus 1. See, the thing is, it's not hard to show that any cat 0 space is contractible. Okay, so I should say this cat 0 implies contractible. Okay, we're almost out of time. Let me stop this session and start a new one. Okay.
Sir, you were on mute.
Yeah.
We can't hear you.
Yeah. So, right. So it's not hard to show that cat0 spaces are contractible. I mean, the proof is, the point is that in a cat0 space, actually there is a unique geodesic joining any 2 points. And this geodesic depends continuously on the endpoints. So you can join every point in the space to a fixed origin, and then you contract the whole space along these geodesics, okay, radially to the origin. So a cat0 space is contractible. Okay. So for a Riemannian manifold, if X is a Riemannian manifold, say a complete Riemannian manifold, okay, so then the curvature of X is less than or equal to minus a squared if and only if X is locally cat minus a squared. So that means every point has a ball around it, which is cat minus a squared. Okay, so not globally, because globally it may not be contractible, right? So for example, I mean, the torus, this is locally cat0, but not globally because it's not contractible, right? And a genus 2 surface will be locally cat minus 1. Okay. Is it clear? Is this clear?
No, I didn't get it.
See, the point is cat0, this is a global condition. This implies contractibility.
Okay. Yeah, that's all right.
Because that's okay, yeah. So what I'm saying is, for a complete Riemannian manifold, I'm not assuming any topological condition like simply connected
Right.
anything. If I just give a Riemannian manifold, then Alexandrov proved also that the sectional curvature is less than or equal to minus a squared if and only if X is locally cat minus a squared. So that means for all X in X, there exists R positive such that the ball BXR is cat minus a squared. So not the whole space, just a ball around the point is cat minus a squared. Is it clear?
Yeah, that is.
So if I take a torus, okay, then the torus is not contractible, right?
Right.
So it cannot be globally cat0. It is just locally cat0.
Yeah.
Okay.
But
So if I take a, yes, go ahead. Yes.
if you increase the genus, then it becomes more cat.
Yeah, well, then it is, if I take a hyperbolic surface of genus 2, then the curvature is constant equal to minus 1,
Yeah.
right? Then it is just locally cat minus 1. That's all. It's just locally cat minus 1.
Okay.
That's all. Yeah. That's all one can say. Yeah, that's all. What you're saying is, see, if you make the, let's say if I take this, say this is my XD, this say genus 2 surface, let me call it sigma 2. Okay. If I rescale this, if I divide the metric by A, okay, so then it becomes much smaller.
Right.
Then the curvature becomes minus a squared. This will be locally cat minus a squared. Okay, so if I divide by a large constant, then the
Hmm.
curvature becomes very negative. So it becomes locally cat minus a squared.
Okay.
Yeah. Okay. All right. So this is about, yeah. So what is the hierarchy then? So in a sense, in this class of spaces, we have, let me forget about the locally cat k spaces and let me talk about global spaces. So let me assume X is so complete simply connected and curvature is less than or equal to -1. So this is contained inside cat -1 spaces, strictly contained. And cat -1 spaces are contained inside cat 0 spaces. Okay. So, and here cat 0 spaces, this also contain, here you have non-positively curved manifolds. So complete simply connected, sectional curvature less than or equal to 0. These are cat 0, but they may not be cat -1. Okay.
Right.
So the rank 1 symmetric spaces, they fit in here. In the complete simply connected, curvature less than or equal to -1. In particular, they are also cat -1, and so they are also cat 0. Okay. Now, in the non-positive curvature manifolds, here you have the higher rank symmetric spaces. So the higher rank symmetric spaces.
I mean, we are assuming non-compact type. Yeah, right.
Non-compact type. Non-compact type. So the higher rank symmetric spaces of non-compact type, and also the Dirac-Ricci spaces. These are all non-positivity curved. Okay. So this is sort of the picture. These are not negatively curved, so they don't fit into cat -1 or manifolds of negative curvature. They are cat 0. That's all. Okay. So is the picture a bit clearer now, Rudrada?
Yeah. Another thing is
And
Gromov hyperbolic space.
right. So that's the last thing to talk about. So Gromov hyperbolic is, so all of these conditions, sectional curvature is an infinitesimal quantity, right?
Right.
It's in terms of small neighborhoods of a point. Cat -1, well, it is both local and global, because cat -1, you're talking about all triangles. So the triangles in the space could be very large, or they could also be very small triangles. Same for cat 0. You're talking about triangles of very large and very small scales. So cat -1, cat 0, these are for all scales. Whereas Gromov hyperbolic is a notion of negative curvature for only large scale, which only looks at large scale properties of the space. So Gromov hyperbolic, that means a geodesic metric space. So there is a more general definition where they are not necessarily geodesic spaces, but let me, for simplicity, give you the definition for geodesic metric spaces. It's a bit simpler there and easier to see. So geodesic metric space such that there exists a delta positive, well, greater than or equal to 0, such that all geodesic triangles are delta thin, i.e., this means that if I take any geodesic triangle, then delta thin means that each side is contained in the union of the delta neighborhoods of the other two sides. So if this is the delta neighborhood of this side, and say this is the delta neighborhood of the other side, then the union of these two delta neighborhoods contains this third side. Okay. And the same is true for any side. Okay. So each side is contained in the delta neighborhood of the union of the other two sides. Now the point, why am I saying this is only about large triangles? Well, as Mohandas used to say, think of delta equal to 100, okay? Then these triangles, if you take a triangle of diameter, let's say less than delta by 2 or something, then this is vacuous. I mean, this is trivially true, right? This delta thin condition is trivially true. So this does not tell you anything about triangles whose diameter is small compared to delta. So you don't get any information at the very small scale. As soon as the triangles are small compared to delta, then you have no information. So, for example, if I tell you that a manifold is Gromov hyperbolic, that does not tell you anything about the sectional curvature, because sectional curvature depends on very small triangles. You cannot detect sectional curvature from triangles above a certain diameter, right? So, for example, okay, so let me say, so cat minus a squared is contained in Gromov hyperbolic if A is positive. So strictly negative curvature bound, upper bound, implies Gromov hyperbolic. Okay. But the converse is not true. So Gromov hyperbolic does not tell you anything about sectional curvature or local curvature bounds. Okay. So for example, the Dimitrici spaces these are non-positively curved, we've already stated here. These are Gromov hyperbolic. Okay, but higher rank space, symmetric spaces, these are not Gromov hyperbolic. And that is easy to see because these are not how do you say not contained in? Yeah, well. Contained. So why are the higher rank symmetric spaces not Gromov hyperbolic? That's because the rank is at least 2. That means they contain convex, isometrically embedded convex copies of R2, right? So these contain R2. And in R2, you have triangles which are arbitrarily large, which are not delta thin, right?
Right.
If I take a delta neighborhood, a fixed neighborhood, it's never going to contain a fixed delta neighborhood is never going to contain the third side, right? If delta is fixed. So R2 is not Gromov hyperbolic. So therefore, any higher rank symmetric space will not be Gromov hyperbolic. Okay, because this copy of R2 inside the symmetric space, this is a convex copy. So that means points in this copy of R2 are joined by geodesics staying inside that copy of R2. Okay, so that means the
Submanifold.
triangle, well, it's a convex submanifold.
Complete.
Convex.
Yeah.
Convex, yeah. The point is convex. So I mean, in this copy of R2, the geodesic joining the points in this copy of R2 stays in this copy of R2. That's what it means to be convex, right? So if it's a convex copy of R2 sitting inside your space, then these geodesic triangles in R2 are also geodesic triangles in the whole space. And then this Gromov hyperbolicity will fail. Yeah.
So far,
yeah.
so far, Gromov hyperbolic space is the largest collection.
Not well, no, that's the thing. It's a bit more complicated. So you see, the cat0 spaces are not necessarily Gromov hyperbolic, right?
Right.
Like the higher rank symmetric spaces, those are cat0 but not Gromov hyperbolic.
Right.
But I mean, cat minus one is contained inside Gromov hyperbolic.
Yeah,
this is true.
That's true.
But there is no containment relation between Gromov hyperbolic and cat0. There's no relation there. I mean, you know, some space could be cat0 and Gromov hyperbolic. Some could be Gromov hyperbolic but not cat0, and so on. So,
Right.
yeah. So, I mean, you see, cat0, suppose I take a manifold. Cat0 implies that the curvature is less than or equal to 0 everywhere. But there are manifolds which have points of positive curvature, but which are still Gromov hyperbolic. So, for example, if I take, let's say, because Gromov hyperbolic is a large...
SN, any compact matrix.
No, compact is a trivial example. That's not a, that's a non-example.
I mean, SN is positively
Don't give
curved,
trivial
right?
examples. Don't give trivial examples. SN is compact. Compact is obviously Gromov hyperbolic. That no one considers compact spaces Gromov hyperbolic. Okay, that's a non-example.
Okay.
I mean, yes, you can say technically, yes, it's an example, but people will, you know, scold you if you do that. Don't. That's not an example. Okay, the compact spaces are not. When you're talking about Gromov hyperbolic, you mean non-compact spaces. So, if you want an example of a non-compact space which is Gromov hyperbolic but has points of positive curvature, what you can do is you take so okay, so you take H2, which is the universal covering of a genus 2 surface, okay. And now what you do is, this genus 2 surface, this has, let's say, constant curvature -1, okay. But what you can do is, you can deform the metric in a neighborhood of a point. Okay, you take a metric which is equal to G0 outside a ball, and in this ball you can deform the metric so that here it becomes sort of positively curved. Okay, so you get some metric KG1, this is positive just in a small ball. Some B x naught epsilon. Okay. Now you lift this to the universal cover. Okay. So you look at H2 with the lift of this metric G1 tilde. Okay. Right. So this will have points of positive curvature. This will have points of positive curvature. Okay, so you have the tiling here by octagons. I'm just drawing a very rough thing. Okay. This is the universal cover. Okay. So in each fundamental domain, you'll have a point of positive curvature. Okay. So there will be lots of points of positive curvature. All right. But this will still be Gromov hyperbolic because this is what is called quasi-isometric. To H2 with the standard metric G0, okay, which is the usual H2 of constant curvature -1, which is cat -1, which is Gromov hyperbolic. Okay, and what one can show is that quasi-isometry preserves the class of Gromov hyperbolic spaces. So if a space is quasi-isometric to a Gromov hyperbolic space, then it is also Gromov hyperbolic. Okay. So this has positive curvature, but at large scale, the large scale triangles, the point is actually both these spaces, these are both quasi-isometric to the Cayley graph of the fundamental group pi1 of sigma 2. Okay, so here you have the Cayley graph. That will be the graph joining these fundamental domains. Okay, so it will not be a tree. It will have loops, but the loops will be small of bounded diameter. And in fact, the Cayley graph will be a Gromov hyperbolic space. And so so even if you have positive curvature, at large scale, the point is that this is, at large scales, it is bi-Lipschitz to the Cayley graph, which is Gromov hyperbolic. And so, you know, these points of positive curvature, they don't matter in the large scale. Okay, so you can still have, yeah, points of positive curvature and still be Gromov hyperbolic. Yeah. So yeah, I mean, the relation between these three is a bit more complicated. So cat -1 is contained inside both Gromov hyperbolic and cat 0. But the relation between cat 0 and Gromov hyperbolic is, there's no containment relation either way. There's no containment relation. Okay. So okay, fine. So yeah, so maybe I just, since in this session we don't have much time, so let me just say a bit about, say, a rank 1 symmetric space. So I wanted to say a bit about the boundary. So take the Cartan decomposition in AK. And so say K is equal to, so G is the isometry group of X, and K is the stabilizer of the origin. Okay. So this is the symmetry group of X, the orientation preserving asymmetry group. And K is the stabilizer of the origin. Then in this Cartan decomposition, what happens is the AT orbit of the origin is a geodesic. Okay. So this is ATO, and let's say this is A minus TO. So what happens is this is a bi-infinite geodesic. So this converges to two endpoints on the boundary, right? So let's call those infinity and 0. Okay. So this ATO, this converges to say infinity as so
Actually, 0 is already there as origin. So
yeah, I know, maybe I should call it something else. Okay, let me just call these okay, let me call these xi and eta. Okay, xi and eta. Yeah, there's the notation will not be good. Okay. Okay, so then this converges to say xi in boundary X as t tends to plus infinity, and eta in boundary X as t tends to minus infinity. Okay. And now you have a K action on X, right? So we saw that any action by isometries, right? This induces an action on the boundary, right? And since we are in rank 1, K acts transitively on the unit tangent sphere at the origin. Okay. And we know that we have this homeomorphism from the unit tangent sphere to the boundary, right? Which sends you take a unit tangent vector, take the corresponding geodesic, and take its forward endpoint, right?
Right.
You have this homeomorphism from the unit tangent sphere to the boundary. And what happens is this homeomorphism is K equivariant. So that means it conjugates the K action on the unit tangent sphere to the K action on the boundary. Right, that's clear because if you know K moves this tangent vector to this tangent vector, then clearly it moves this geodesic ray to this geodesic ray, and so it moves this boundary endpoint to this boundary endpoint. Is this clear?
right.
Yeah. So this action on the unit tangent sphere, this is transitive. So therefore, the action on boundary X is also transitive. Okay. This is an equivariant map.
So only in rank 1.
This is only in rank 1. This is only in rank 1. This is only in rank 1. Yeah. So therefore, since it's a transitive action, so thus boundary X is homeomorphic
Okay.
to K modulo the stabilizer of a point. So this M is equal to the stabilizer in K of xi.
Right.
Okay. Okay. Now, what is the stabilizer in K of xi? Well, K already fixes the origin. So if a point in if an element of K fixes xi, then it's going to fix the geodesic ray from 0 to xi. So therefore, it's going to fix the bi-infinite geodesic. So therefore, it's going to fix both xi and eta, right?
Right.
It's going to fix both xi and eta. So this is actually the same thing as the stabilizer in K. So, and it's going to fix every point on gamma, right? Because it fixes the origin and it preserves distance along gamma. So therefore, it's going to fix every point along gamma, right? Is that clear?
Yes, sir.
Okay, so this is a stabilizer, I mean, of gamma. I mean, when I say stabilizer of gamma, I mean pointwise. Okay, so not as a set, but pointwise.
That means every point of A is stabilized, right?
Well, every point of the A orbit, not A, but every point of the
A
A
orbit,
orbit is fixed. Every point of the A orbit is fixed, yeah. Right. So, I mean, so if K belongs to M, so I mean, let me just write this way. K belongs to M if and only if K ATO is equal to ATO for all T. Okay. So you preserve this geodesic. So what does that mean? That means, so in particular, I preserve this unit tangent vector pointing towards xi, right? So if I look at the action of the derivative, right? So if I fix this geodesic, then this unit tangent vector is fixed and the derivative is an isometry of this tangent space to itself. So therefore, it preserves the orthogonal complement, right? Okay, so therefore, because it's an isometry, it's going to preserve the exponential of the orthogonal complement. Okay, so when I take the exponential, I'll get a an n-1 dimensional subspace. This is invariant under M. So M will do what? M will act as rotations around this geodesic. Okay, so M is a group of rotations around this geodesic. So for example, if X is equal to real hyperbolic space, then K is equal to SON and M will be equal to what? Well, this vector is fixed, so then it will be an
SON minus 1.
SON minus 1, right? So M will be SON minus 1. Okay, so these will be rotations around this fixed axis. Okay, so that is the group M. And the boundary is then K modulo M because the action is transitive and M is the stabilizer of a point. So that's in K. So yeah, this is the picture I wanted to give. So this is how one identifies the boundary with K mod M. Is this okay? So yeah. Okay, so here boundary X, this is Sn minus 1, which is the same as SON mod SON minus. Okay. All right. So yeah, so this is more or less what I wanted to say. Any questions?
So you will call this visible boundary or something, right? I mean, you said
A visual boundary.
visual
Yeah,
boundary.
visual boundary.
Yeah.
Visual boundary, right.
Hmm.
In terms of, because it's in terms of geodesic rays.
Right.
So
Yes.
that's why it's called visual boundary. Yeah. Right. There are other boundaries like the Martin boundary. That's in terms of positive harmonic functions.
Yeah.
So
Analytic.
Then there's also the Poisson boundary. The Poisson boundary is in terms of bounded harmonic functions.
Right.
So, yeah. But this is the visual boundary.
Hmm.
I mean, so for a higher rank symmetric spaces, those are cat 0.
Hmm.
But there, the visual boundary, see, for any manifold of simply connected, complete of non-positive curvature, as we saw last time or yesterday, the visual boundary is always topologically a sphere, Sn minus 1, right? You have the map from the unit tangent sphere at a point to the boundary. That map is always a homeomorphism. So the boundary is always a sphere topologically, an n minus 1 sphere. But this K mod M for higher rank symmetric spaces is no longer a sphere topologically. It's no longer a sphere. So these two, K mod M turns out to be the Poisson boundary for higher rank symmetric spaces.
Okay.
But that is different from the visual boundary. It is different from the visual boundary. Yeah. Yeah, so for higher rank, these boundaries become different. For rank 1, they're the same. There's Poisson boundary, Martin boundary, visual boundary. They all are, they can be identified.
So K by M is much thinner, right? I mean, in higher rank.
Yeah, in a sense, in higher rank, it's smaller. Yeah, in a sense, yeah. In a sense, it is smaller. Yeah. Yeah, something like that. I don't know exactly what the topology of K by M is in higher rank. Maybe I'll ask Mohan if he knows. Yeah. Yeah. Okay, so there's just one session left. So let's stop this and start another one. I'll just take a 2-minute break. Okay. Okay. There's less than a minute left. So let me stop this. Yeah. Okay, so any more questions about this boundaries and symmetric spaces and so on? Yeah, so just one thing I should say, which Rudra was also hinting at, is that this M is also the centralizer of AT. So this is if and only if KAT equal to ATK for T.
For Dimitrich spaces, there is no M, right?
That's a good question. There is some M which could be smaller than for symmetric spaces. So the M is it's a group of automorphisms of N. It's a group of automorphisms of N. For Dimitrich spaces. I think M is equal to I need to check this. I'm not sure about this. Okay. I think it is the centralizer of AT of A inside aught N. So A acts on N by automorphisms, right? So M is identified with a subgroup of aught N.
Okay.
I think that is so right. So see, for any symmetric space, K is always identified with a subgroup of SON, because you look at the action on the unit tangent, you look at the action on the tangent space at the origin, right? So that identifies K with a subgroup of SON, and M will fix this geodesic. So it's going to fix a unit vector. So therefore, M becomes a automorphisms of the orthogonal complement. So M is identified with a subgroup of SON minus 1. So in general, these are not equalities, these are containments. Yeah. So for Dimitrici spaces, this M that you get will be some subgroup of SON minus 1.
Okay.
Yeah. So, I mean, you have the same picture for Dimitrici spaces that the AT orbit of the origin is a geodesic. There's a point at infinity, and there's a, well, let me call this a big zero. Okay, there's an opposite point here, and M acts again as rotations around this geodesic. So on the boundary, it has two fixed points, 0 and infinity. And on the boundary, it acts as sort of rotations. Yeah. So M will fix the norm on the Heisenberg group, or the norm on N, the anisotropic norm. M will act as isometries for the norm, the anisotropic norm. Yeah. On N. That is true, I think. Yeah. Any more questions? I'll look this up. I'm not exactly sure if this is equal to the centralizer of A. I think so, but I have to check this. I'm not sure. There is a group M, which is a subgroup of Auten, which is a compact group. So A is a non-compact group inside Auten, but this M is a compact subgroup of Auten. That is there. There is such a group.
Can we comment anything about its Lie structure?
M.
M, yeah.
Well, I don't know anything. It's a compact group, which is, a subgroup of SON minus 1. That's about all I think one can say. I don't think much more is, that's all I know, at least. I don't know more. Maybe the experts know more. I don't know. Yeah. I don't know anymore. But... Okay. So, all right. So let's now come back to the Dirichlet problem at infinity. Okay. So, one second. Let me just. Okay. All right. So I've already stated last time what is the Dirichlet problem at infinity, right? So you have a negatively complete simply connected manifold of pinched negative curvature, and so you have its visual boundary. You have a continuous function on the visual boundary. You want to extend it continuously to a harmonic function in the whole space, in the inside, right? So a key point in this is looking at the distance function from a point and using that to construct superharmonic and subharmonic functions. So how do we do that? So fix a point P and M and let rho P be of X be the function distance from X to P. Okay. So we know this distance function is smooth outside the point P, right? This is smooth on M minus P. And the norm of the gradient of this function is 1, right? The gradient vector field is just the radial vector field, which points outward from P. And we also have the Hessian comparison theorem. Because the curvature is bounded above and below by negative constants, right?
Yeah.
The Hessian nabla squared rho of WW at a point Q, this is bounded above and below, right? By A cottage A rho into the norm of the normal component of W squared, and B cottage B rho into the norm of the normal component of W squared, where what is this normal component? You take a point Q in M minus P. So then you have the gradient vector of this distance function at Q. That is your radial vector. And the normal component is the component in the orthogonal complement of the gradient vector. Okay. So you write any W as W tangential plus W normal. Okay. With respect to this direct sum decomposition, the span of the gradient vector plus its orthogonal complement. Okay. So this normal component is the component which is tangent to the geodesic sphere passing through Q. All right. And with center P. Is that clear? Yeah.
Right.
Okay. So we have this upper and lower bound on the Hessian, and we know that the Laplacian is the trace of the Hessian. So the trace means you sum up the Hessian applied to EI, EI, where EIs are an orthonormal basis, right? So you choose the orthonormal basis to be of the form, the first vector is the gradient vector, and then you take a basis of the orthogonal complement. Okay. So then in the direction of the gradient vector, right, along the integral curves of the gradient vector are just geodesics starting from P, right? So along those geodesics, the distance function is just a linear function, T. I mean, rho of gamma T is equal to T. So the second derivative is 0, right? So the Hessian is 0 along the direction of the gradient vector. That you can also see from this estimate, because the normal component is 0 in the direction of the gradient vector. So when you sum up when you take the trace, you get a 0 from the radial direction. And then in these n-1 directions, you'll get upper and lower bounds. And so you'll get that the Laplacian is bounded below by n-1 times A cottage A rho, and bounded above by n-1 times B cottage B rho. Is this clear? Yeah?
Yes, sir.
Okay. So you have upper and lower bounds on the Laplacian of the distance function. And using this, so if we write rho as this rho P, okay, let's just write rho from here. So then we can work out the Laplacian of e to the minus delta rho, right? So we worked out a change of variables formula, remember? For Laplacian of a real valued function u composed with a function phi on the manifold. That was u double prime into norm of phi squared, norm grad phi squared, plus u prime into Laplacian phi. So if you apply that composition formula, then you'll get the Laplacian is, you differentiate this e to the minus delta t twice, you'll get delta squared e to the minus delta rho into norm grad rho squared, and differentiate once, so you'll get minus delta e to the minus delta rho into Laplacian rho. So this becomes delta squared minus delta into Laplacian rho into e to the minus delta rho. And now we can use the lower bound on the Laplacian. This is greater than or equal to n minus 1 into a times cot h a rho. And cot h is always bigger than 1 because it's cos h over sin h. So this is greater than or equal to n minus 1 times a. And so the Laplacian of e to the minus delta rho will be less than or equal to delta into delta minus n minus 1 a e to the minus delta rho, right? Okay. So in particular, if delta is very small compared to a, that is, if delta is less than or equal to n minus 1 times a, then the Laplacian of this e to the minus delta rho will be less than or equal to 0, right? Okay. So that means that e to the minus delta rho, this is going to be superharmonic on m minus the point p, if delta is less than or equal to n minus 1 times a. Is that clear? Yeah.
Yes.
So if this e to the minus delta rho, this is continuous on all of m. So then it's easy to show that if you have a function which is continuous on the whole manifold and superharmonic outside a point, then it is superharmonic on the whole manifold. So how do you see that? Well, you can use the following argument. For epsilon small, you define this function f epsilon of x. This is the minimum of e to the minus delta rho x and 1 minus epsilon. So if x is close enough to the point, to the origin, then this e to the minus delta rho x is close to 1. So it's going to be bigger than 1 minus epsilon. So this minimum will become 1 minus epsilon. So this function is constant in a neighborhood of the origin, right? Equal to 1 minus epsilon. So in a neighborhood of the origin, it will be superharmonic. It's constant there. And if you're outside the neighborhood of the origin, then locally it is the minimum of two superharmonic functions. Therefore, it is superharmonic, right? Okay.
Yes.
Okay. So these functions f epsilon, these are superharmonic. And as epsilon tends to 0, you can see these converge uniformly to e to the minus delta rho, right? And so a uniform limit of superharmonic functions will also be superharmonic. Okay. Yeah, I mean, that
Yes,
you can
yes.
see using the fact superharmonic is equivalent to what we proved, that the value at the center of a ball is greater than or equal to the integral with respect to harmonic measure on a small sphere around the ball, right?
Yes.
On
Yes.
every small sphere around the ball. So if you use that, then you'll see that is preserved under uniform convergence, right? So therefore a uniform limit of superharmonic functions will be superharmonic. Okay. So this e to the minus delta rho, this is superharmonic. Okay. And so we note we have this estimate that the Laplacian of e to the minus delta rho, this is less than or equal to minus n minus 1 a over 2 into delta into e to the minus delta rho, if delta is less than or equal to half n minus 1 into a. Okay. Yeah, that follows from this inequality here. Okay. All right. So let's just note this. Okay. Fine. Okay. So now I need to talk a bit about Riemannian angles and comparison angles. Okay. So Riemannian angles between 2 points x and y with respect to a base point P, the angle theta P of xy means you take the unique geodesics from P to x and P to y, and you look at the angle between these geodesics at the point P, That means the angle between their tangent vectors at P. Okay. All right. And then we can also talk about comparison angle at P. That means you take the unique geodesic triangle, okay, in the model space of constant curvature minus a squared. Okay. So there is a unique geodesic triangle delta bar with vertices p bar, x bar, y bar, which has the same distances as in the manifold M. Okay. So this triangle delta bar is, as we've described earlier, a comparison triangle for the geodesic triangle delta in M. And then we define the comparison angle theta p minus a squared xy to be the angle between the angle at p bar in the model space. Okay. Is it clear? Yeah.
Yeah.
So that means the angle in the comparison triangle. Okay. And then we have the following fact, which we will use without proof, that this upper bound on curvature, curvature less than or equal to minus a squared, this implies that the Riemannian angle is less than or equal to the comparison angle. Okay. So this follows from the fact that the manifold M is cat minus a squared. It follows from that. So, yeah. So Riemannian angles are smaller than comparison angles. Okay. So now we come to the solution of the Dirichlet problem for a Lipschitz function on boundary. Okay. So you fix an origin P and M, and you consider del M equipped with the angle metric theta P. So theta P means that is the angle between the geodesic rays going to two boundary points. So if this is P and you take 2 points on the boundary, xi and eta, then you know that you have unique geodesic rays going up to xi and going up to eta. And theta P of xi eta is the angle between these two. Okay. So the angle between these two geodesic rays. So theta P of xi eta is defined to be theta. So this is in the interval 0 pi. Okay. And so this theta P, this is a metric on boundary M. Okay. All right. So now you take a function phi on boundary M equipped with this angle metric, which is a Lipschitz function. Okay. So that means there's a constant C positive such that phi xi minus phi eta is less than or equal to a constant C times theta P of xi eta. Okay. So now what we do is we define a function phi bar on M bar minus the point P, which is the radial extension of phi. So that means what you do is you join all points on the boundary to the origin P by geodesics. Okay. And you just define phi bar to be constant equal to phi on each of these geodesics. So that means if this is a point xi and I take a point x here, then phi bar of x is defined to be phi of xi. Okay, so phi bar of x is defined to be phi of xi for all x in the open geodesic ray P to xi for all xi in boundary M. Okay, so you just extend it to be constant along geodesic rays from P. All right. So this is a radial extension. Okay. And this function is not smooth in general, right? Phi is just some Lipschitz function on the boundary, and this will not be a smooth function. So what we want to do is take a smoothing of this. Okay, so if we were in Rn, we could take a smoothing by convolution. So here we will do something similar to a convolution to get a smooth function. Okay. So notice though, this function phi bar, this is constant on geodesics through the origin. It is continuous on m bar minus the point P, and restricted to boundary M, it is equal to phi. Okay. All right. So now we need the following lemma, that if x is a point at distance at least 3 from the origin P, then phi bar x minus phi bar y is less than or equal to some constant C prime into e to the minus a rho x. Okay. For all y in the ball of radius 2 around x. Okay. So this rho x is the distance of from x to P. Okay. So what does this mean? This means that if I take x, which is outside a ball of radius 3 around P, and I take a ball of radius 2 around x, then if I take a point y here, then phi bar x minus phi bar y, this is less than or equal to constant times e to the minus a rho x. Okay. Okay, so how does one prove this? So, okay. So to prove this, we'll use the properties of Riemannian angles versus comparison angles. Okay. So suppose the distance from x to P is greater than or equal to 3, and let y be a point in the ball of radius 2 around x. Then that means both rho x and rho y are greater than or equal to 1, right? By the triangle inequality. So now you take a comparison triangle, delta bar, in the model space of constant curvature minus a square, with vertices p bar, x bar, and y bar. Okay. And so the side lengths, let's say s is the distance from p bar to x bar, that is rho of x. T is the distance from p bar to y bar, that is rho of y. And r is the distance from x bar to y bar, that is equal to the distance from x to y, that is less than or equal to 2. Okay. So let me draw a picture. So in my space, I have x, y. So this distance is s, this distance is t, and this distance is r. Okay. And let's say when I extend the geodesic from x to infinity, I get a boundary point xi, and here I get a boundary point eta. And now I'm looking at a comparison angle in the models, a comparison triangle in the model space. So P bar, X bar, Y bar. So these distances are also S, T, and R. So this angle here, theta, this is the comparison angle, okay? And we have this hyperbolic law of cosine. For the model space H2 of constant curvature minus a squared, it says that cos h of, so this theta is equal to the comparison angle, theta p minus a squared xy. Yeah. So, so cos h of AR is equal to cos h AS cos h AT minus sin h AS sin h AT cos theta. Okay. This is the hyperbolic law of cosine. So what I'll do is I'll rewrite this hyperbolic law of cosine in the following form. You write cos theta as 1 minus 2 sine squared theta, sine squared half theta. Okay. And so then this will become cos h of AS cos h AT minus sin h AS sin h AT. That becomes cos h of A times S minus T. And then you get plus 2 times sin h AS sin h AT sine squared half theta. Okay. All right. So S and T are my, so here S is equal to rho X and T is equal to rho Y. Yeah. And so both of these are greater than or equal to 1. Okay. So then that means that sin h AS and sin h AT will be bigger than a constant times e to the AS and e to the AT. Okay. So I substitute that here. This will be bigger than cos h AS minus T plus 2 e to the AS e to the AT sine squared theta by 2 into some constant squared. And this cos h is bigger than 1. So this is bigger than 1 plus 2 constant squared e to the what is this? This should be e to the this should be e to the AT. E to the AT. Sorry, this is a typo here. Yeah, this is e to the AS, e to the AT. Oh, right. Oh, okay. No, I see what I've done. Yeah. Okay, fine. Yeah. So this. Okay. So here, this S and T. So okay. Let me just do this here. This is greater than or equal to 1 plus 2 constant squared e to the as e to the at sine squared theta by 2. And here S and T mod S minus T, this is by the triangle inequality less than or equal to the distance between x and y, which is less than or equal to 2. So that means T is bigger than S minus 2, right? So T is bigger than S minus 2. So if I substitute that here, then I'll get this is bigger than 1 plus 2 times a constant square times e to the 2as e to the minus 2a sine squared theta by 2. Okay. And r here is less than or equal to 2, right? This distance xy, this is r. So this is less than a constant, c. Okay. So for S large, this means that theta is less than some constant times e to the minus as, right? Is that clear? Yeah. Okay. Yes.
Yes.
Right. So this comparison angle is less than this constant times e to the minus as. But we know that the comparison angle is greater than or equal to the Riemannian angle, right? So that means the Riemannian angle, theta p xy, this is less than or equal to theta, which is less than or equal to c2 e to the minus as, right? But this Riemannian angle here, this is the same as the angle metric between xi and eta, right? This Riemannian angle here. And you know that phi is Lipschitz with respect to the angle metric. So therefore you get what we want, right? You get that from this you get that phi bar x minus phi bar y, this is less than or equal to constant time as well. This is equal to phi xi minus phi eta and that is less than or equal to constant times theta p of xi eta, since phi was Lipschitz, and theta p xi eta is the same as theta p xy, and that is less than some other constant c prime times e to the minus as. Is this clear? Yeah.
Yes, sir.
Okay. So that proves the lemma. Okay. That proves the lemma. Okay. All right. So we're almost out of time. But what we're going to do next is basically define a sort of convolution. So we'll get a smooth function. Okay. So we'll define a convolution. I'll do this next time. And you get a smooth function whose first and second derivatives will decay exponentially near infinity. So its Laplacian will decay exponentially near infinity. And then if you add e to the minus delta rho, a large multiple of e to the minus delta rho, that the Laplacian we know is negative. and it will be large and negative, and it will so this smooth function plus a large constant times e to the minus delta rho, that will be a superharmonic function, which will be bigger than phi near the boundary. So that you can use as a barrier. Okay, and we'll use the Perron method then to solve the Dirichlet problem. So, okay, so if you want me to say more, I can continue. Others we'll continue next Tuesday. So okay, fine. Let's just continue next Tuesday. We'll finish next Tuesday. We can finish then. Okay. So let me stop here.